Well, hello again. We're going to talk about lipid health concerns today, which basically boils down to heart disease. So we're going to look at the aspects of heart disease, and it could get a little bit technical. So I will try to do my best to make it as clear as possible, but there's just a lot to it. We're going to get into oxidation. We're going to get into the liver cell. We're going to talk about the lipoproteins that we just finished with, and get you more up to date on where nutrition fits into the scheme of reducing risk of heart disease. Cardiovascular disease, disease of the heart and the circulatory system. Um, Basically, it has to do with not getting enough oxygen to your myocardium, which is the heart muscle, and the muscle needs, oxygen to make ATP 24/7. So if you deplete the oxygen to the heart muscle, then it's going to quit working and basically it can die. And that's where you get a heart attack, and just in a small section of your heart. It doesn't have to be the whole heart, it's just one little section that's not going to contract, and you've got problems. So it's whatever can restrict the ability of getting oxygen to those muscle cells. That is going to be a problem, and that will relate to plaque, which relates to nutrition that we'll be talking about. Just real quickly, you can see how many deaths there are. We talked earlier in class about heart disease is number one. But you can look at the risk factors: high blood pressure, high LDL cholesterol, smoking, and they say 49% of people live in this country have at least one of these three risk factors, and 37 have more than one of those risk factors. So it's pretty prevalent, and it's not going anywhere. It's not going down. Again, you can see if you look down in this area of the country, you can see we looked at where the highest obesity rates were. We looked at where the least activity was. And now we're looking at the highest risk of heart disease. And basically, I'm pretty sure you'd find diabetes being the highest ones in those areas too. So anyway, if you don't want to get heart disease, don't move to those areas or don't live like them. National costs, you can see it's quite a bit of money, 28, and this is only for the care, and a lot of it has to do with heroic means, which basically means surgery that people would be going through, but a lot of medications and that kind of thing. So a lot of money spent per year. That does have a nutrition basis that could reduce this cost if people would do what they need to do. So we'll talk about what needs to happen. Hypercholesterolemia, basically hyper means high, cholesterol means cholesterol, and emia means in the blood. And so the main nutritional risk factors, hypercholesterolemia, as far as nutrition is concerned. Obviously, smoking would be in the top of the list. It's not nutritional. But hypercholesterolemia, because LDLs, if you remember, have a high amount of cholesterol, is basically going to be the levels of LDLs is going to determine hypercholesterolemia. And the risk of this is that you have a high risk of plaque buildup in the arteries, and we'll talk about plaque. But let me just show you a picture. Here's the plaque right here, and you can see it's closing off the artery. And what we just talked about was that if you close off the artery enough, you're not getting enough oxygen, then it's going to lead to a heart attack. So what are the factors affecting hypercholesterolemia? It could be intake of cholesterol, which is significant, but not as significant as saturated fat. Saturated fat is the big player in determining hypercholesterolemia, and we'll talk about that. But so eating, actually, what they've done studies where they actually everything stayed the same except they just increased cholesterol, didn't have a huge effect. But if you increase saturated fat, it does have a huge effect. We talked about total calories, where the total calories can turn to fat in the liver, become VLDLs, eventually become LDLs. And then soluble fiber, when we were talking about fibers, we talked about how fiber can bind onto the cholesterol, dietary cholesterol, and for some people it will reduce. But if your cholesterol problem is not a dietary problem, which sometimes it is, then soluble fiber is not going to do much for you. So it's something else. Absorption rate, there is a different amount of percentage absorption between people, and it ranges from 25% to 75%. So if you're very efficient at absorbing cholesterol, then that could be a problem for you. You could, be very efficient at something that's not good to be efficient at. And then endogenous synthesis basically means how much does the liver make. The liver can make cholesterol. It actually makes 80% of the cholesterol that's in our body. So that's endogenous synthesis. And so if your liver is making too much, or if it's an issue with how much is made, then your diet wouldn't be an issue. So diet is not always the problem, but it can be a significant player in the whole scheme of things. So there are people, different levels that have different homeostasis levels of LDL. Some people just have a high LDL homeostasis. And so it doesn't matter, what they eat. It's just that if you don't eat cholesterol, then your body says, well, I'll just make more. If you eat more, say, I'll make less. It doesn't matter to me. You do what you want, but there's a specific homeostasis. And just like diabetes or, sugar levels, everybody's different. And so it's going to be the same thing with LDLs and hypercholesterolemia. So cholesterol is good for your clogs, for you, and doesn't, so you don't bleed so much. It makes you thick, like your blood's like gravy. So I guess that's good. We've already talked a little bit about metabolic syndrome, and we talked about visceral obesity. We've talked about atherogenic dyslipidemia, which basically elevated triglycerides. Again, we talked a little bit about where VLDLs can be an indicator of triglycerides in your body, and lipoproteins. The small dense LDLs, remember we talked about those. Those are a big issue. And then low HDLs, high blood pressure, and insulin resistance. Any three of those factors, if you remember, are going to be just as important. The example of how these would be important is if you have low LDL numbers and low hypercholesterolemia, but you have three of the symptoms of metabolic syndrome, then you are just as high a risk as somebody who has high LDL. So that's why it's important not just to look at your lipid profiles and LDL numbers, but to actually look at the overall picture of your triglycerides and LDLs and HDLs and stuff. So that would be part of the lipid panel, as well as, getting your blood pressure done and that kind of thing. So in hospitals, we kind of talked about it before, that they go through an accreditation process where a group of accreditors will come into the hospital. They'll look through patients' records. They'll look at what you're doing for patients, and they'll basically look at the whole hospital, all the way down to the cleaning department, if it's clean and stuff like that. But when they're looking at heart disease, basically what they're looking at is, did the healthcare team address the primary target? And the case for nutrition, the primary target is going to be to lower LDL cholesterol. Again, what I kind of mentioned before when we were talking about this is, it's not as important that you actually reach the goal for every patient, but the goal is that you have done everything that you can possibly do to lower the LDL cholesterol. A dietitian has consulted and put the patient on a specific dietary regime that is specifically pointed towards lowering LDL cholesterol. If necessary, medications were prescribed to lower LDL cholesterol. Whatever it takes, talk about exercise to raise HDLs and stuff, but our primary goal is to try to get our LDL cholesterol below 100 milligrams per deciliter. That's the goal. So whatever it takes to reach that goal is what the accreditation team will expect you to see, and that's what they would see documented in the patient's chart, that you've tried to reach this goal. So that's the primary target. Now, we talked a little bit about, when we were in the lipoproteins, that the liver cells monitor LDL numbers. So they are going to monitor the homeostasis of the LDL numbers. If the LDLs are too high, then they are going to phagocytize those and bring them in and basically tear them apart. The lysosome will break them apart, and then you lower the blood levels of LDLs, because the higher the amount of LDLs that are in the blood system, the higher risk of, well, we're going to talk about oxidation, but the higher risk of plaque formation. So you need to reduce those, and so there's a certain homeostatic level that your body has. But there are some things that can affect whether the liver cell is able to take those out or not, and that's kind of the direction we're heading right now, is to look at some of the situations where LDL numbers will be maintained high in the blood system, and because the liver can't take them out. So let's look at the different pathways by which LDLs can be taken out of the blood. We talked about one of the lipoproteins, and you saw the arrow where one of the directions that the LDL can go is to the cells, to deliver cholesterol to the cells for everyday purposes, for making, putting cholesterol into the plasma membranes, to making hormones and different things like that. And this is referred to as the cell receptor pathway, where the identification markers on the B100s will match up with a receptor on peripheral cells, which is cells out in your body, somatic cells, so forth. And they're going to deliver they're going to attach there, the cells will take them up, and basically the cholesterol will be used by the cells for growth and development. So this is this is a good way, this is the way you want LDLs to go. The liver receptor pathway would be if LDL numbers are high, then the liver comes into play, where it is going to take LDLs out of the blood. And so we're going to refer to that as the liver receptor pathway as opposed to the cell receptor pathway, even though we are talking about liver cells. So the liver is supposed to be monitoring and maintaining the homeostasis of LDLs in the blood. And so it has B100 receptors that are going to match up with the B100 identification markers, and to maintain homeostasis, but also for cholesterol that the liver may need for its normal function for that. So here what I'm showing you is just kind of a rendition of one liver cell. So this represents one liver cell. And so the way that the liver would take up the LDL is that if the circulating levels or LDL are high, then the liver is, I don't remember from cell biology, if you took it from me, that we basically said that cells can add or take away plasma membrane proteins as needed. And so in this case, the liver cell can add LDL receptors to its plasma membrane, and therefore there would be a higher chance that it's going to attach to an LDL identification marker, and then phagocytize that LDL, bring it in, and then the lysosome is going to break it down and digest it. So you've lowered the level of LDLs in your blood, and then you can deal with the cholesterol inside the cell. But this is a situation where we're going to deal with de-esterifying the cholesterol to make it free cholesterol so it's active and usable. Remember, we said that esterified cholesterol is not usable. It's made for storage or transport. And so the free cholesterol is going to allow it to be used to make hormones or whatever we want. So here's the picture idea of it. And so you see here we have high LDLs in the blood. The liver cell is going to make the receptors. You can see the LDL receptors there, and it's going to make the receptors, and then they're going to match up with the identification markers. They're going to bring the LDL into the cell. The lysosome is going to attach to it. It's going to basically destroy the LDL, and you can see the amino acids from the identification marker being released. The cholesterol is being released. It's going to be de-esterified. So you can see now it's free cholesterol. Up above here, what you see, it has a little tail on it. And so the little tail is the fatty acid that makes it an esterified cholesterol. So you'll notice when we get to the free cholesterol here, it doesn't have any tails anymore. So the LDLs have, or the cholesterol has been de-esterified, and now it's free cholesterol, which means, as you can see, it can be used for putting in cell membranes, for steroid hormones, for making bile. those kinds of things. So it's free to be active. But there's only so much free cholesterol that a liver cell can handle. So if free cholesterol accumulates, so there's too much, basically you've got a high LDL so high that you're taking in so many LDLs, the liver cell can only take in so much free cholesterol. It only has a certain capacity for free cholesterol. So what's going to happen is it's basically going to cause the liver to shut down taking in LDL numbers. And so it will basically reduce the number of LDL receptors so it doesn't take any more LDLs in because it has enough free cholesterol that it doesn't want any more LDLs. It's full, basically. So let's look at the picture on that. So we have the free cholesterol, but what you'll notice is that the free cholesterol, if there's an oversupply of the free cholesterol, which basically means you have brought in enough LDLs and you don't want to bring in any more, if you have an oversupply, there's three things that are going to happen. Number one, as we mentioned, the liver can make its own cholesterol, but basically what's going to happen is the oversupply of cholesterol is going to send a signal to inhibit the ability of the liver cell to make cholesterol, because you've got enough cholesterol, you don't want to make any more, and so it's going to limit the ability of it to make. So that's number one. So it shuts down the liver's ability to make cholesterol. It's going to stimulate the ACAT pathway that is going to esterify the free cholesterol and basically store it as cholesterol esters. So it's going to take some of the free cholesterol and store it, and eventually these will become part of a VLDL. But right now it's going to store it and just get rid of some of that free cholesterol because it has too much. And then the next thing that's going to happen is it's going to inhibit the ability to make LDL receptors. So it's going to reduce the amount of LDL receptors in the plasma membrane, because as you can see, what this shows is the DNA made into RNA. So we're going through transcription, then we're going to go through translation with the ribosomes and the rough ER and all that kind of stuff, and we're going to make receptors, go to the Golgi body, and then embed them into the plasma membrane. But this is going to be inhibited, so this is not going to happen. So the three things are that you're going to reduce or stop the production of cholesterol by the liver cell. You're going to esterify some of the free cholesterol and you put it into storage, and then you're going to stop the ability of the cell to make LDL receptors. Okay, so that's the normal way that you would deal with that, and so you would not take any more LDL out of the blood. Okay, so this is not going to happen. Okay, so that would be the normal liver receptor pathway, but let's look at some things that would affect the ability of the liver cell to actually do that, and one is called familial cholesterolemia. Basically, in genetics, you learned about alleles and genes, basically, and familial cholesterolemia is a genetic disease where it reduces the ability of liver cells to make receptors, LDL receptors specifically. And so if you are basically heterozygote for this allele, then you're going to make half the number of receptors on a normal basis. So you'd only take out half the number of LDLs. If you're homozygous recessive for the allele, then you're not going to make any receptors and your LDL numbers would be really high. That doesn't mean that's a death sentence. What that means is it's a higher risk of those being oxidized and becoming part of plaque, but it's not a death sentence. Another way that you can reduce, and I don't know if you can read this or not, but you can reduce the ability of liver cells to take in LDLs, or actually you're going to increase, sorry, let me go back and start over again. Something like Lipitor is going to actually increase the ability of liver cells to take up LDLs. And the way it's going to do that is to reduce the ability of the liver cell to make its own cholesterol. Therefore, the liver cell is going to want to bring more cholesterol in through the LDL receptor pathway and get some more free cholesterol, because normally, as I mentioned, the liver cell makes 80% of the free cholesterol that our body needs. And so if you shut down its ability to make the free cholesterol, then it's going to have to do something to get cholesterol that it needs, and what it's going to do is make more LDL receptors and bring in more LDLs. So that's the way that these statin drugs work. And let me show you the picture of that with the cell that we just looked at. Basically, Lipitor is going to reduce the ability of HMG-CoA reductase to make cholesterol. So it won't be able to make free cholesterol. Therefore, what's going to happen is you are going to have an undersupply of cholesterol. So you'll have low free cholesterol, which basically does just the opposite of if you had an oversupply. It's going to activate the cell to make more LDL receptors. So when you make more LDL receptors and you put more, then you're going to bring in more LDLs, and then you're going to increase the free cholesterol. So Lipitor basically, again, inhibits the liver cell from being able to make its own cholesterol. So what it's going to do is activate the ability to make more LDL receptors to bring more LDLs in to get more cholesterol. So therefore, Lipitor would reduce LDL numbers in your blood. So that's how it works. And that's also why you have to get a liver test for when you're on statin drugs, because they want to make sure it's not screwing up your liver cells. Okay. So anyway, so that's kind of cool. The scavenger pathway basically is the bad way. Okay, the scavenger pathway is the way you don't want LDL to go, because that is what's going to increase the risk of plaque formation. But the scavenger pathway is going to work on oxidized LDLs. It's going to like we mentioned before, LDLs that are not oxidized are basically benign. Oxidized LDLs are at high risk of being gobbled up by scavenger white blood cells, because what we're going to see is that the identification marker on the LDL is changed by the oxidation, and so it's changed in such a way that the scavenger white blood cells are going to see the identification marker as being foreign. And if you remember, in biology, you should have learned that all your cells have identification markers, and the way that your immune system works is if it sees a marker that isn't yours, then it will try to deal with it and get rid of it. So the oxidized LDLs, the identification markers, the B100, will be changed in such a way that it will be identified as by your immune system as being a foreign object that needs to be gotten rid of. And the way it's gotten rid of is through what are called scavenger white blood cells that are embedded into the blood vessels. So this is kind of the idea of the scavenger pathway, and I've kind of highlighted the big things in red. And is that modification will change the B100 marker. The scavengers will detect this change and engulf the modified LDLs. The ones that are going to be the main problem, though, again, are going to be the small, dense LDLs, and so we'll talk a little bit about those, that process. But what's going to be oxidized is the identification marker is going to be a protein. Remember, it's apolipoprotein. And so the specific amino acid that they found that is going to be oxidized is tyrosine. And tyrosine has some hydroxyl groups here that you can see here and here that are, hydroxyl groups are easily reduced, so they can be oxidized pretty easily. Plus you have this double bond on this oxygen here. So this is an amino acid that can be pretty easily oxidized by free radicals, and you've seen this before, this oxidative rancidity. We talked about it before. But if you can just place the tyrosine in that mix, then you can see where it could be oxidized, where we're going to lead to a hydroperoxide basically here on here. Instead of the double bonded carbons, we're going to just be dealing with the hydroxyl groups that are going to be already formed. Like in here, we're going to form a peroxide there, basically causing it to be oxidized. So that's what changes the identification marker, is the oxidation of the tyrosine. So here's another slide that basically says that the small LDL particles are the most atherogenic. They're going to be the most problem. They're going to be the most attracted to free radicals. They're going to be have the most ability to get through the intima of the blood vessel and become part of plaque. So they don't really do a test yet for small dense LDL particles. I don't know why, whether it's too expensive or they just don't do them. Now it's pretty much a blanket if your LDLs are high, because of who we are as in this country, how we eat and how we don't exercise and stuff. The assumption is made that if we have high LDL numbers, a good portion of them are small dense LDLs, and so we basically attack the high LDL number with that assumption. But you would think they would come up with a good, at least not expensive test for small LDLs, just to see, because if your LDLs are buoyant, then it's not a big deal. As far as we know now, it's the small ones that are going to be the problem. So again, I just show you the picture of the small LDLs are going to be the issue. And here's how the works. If you can look at normal sized LDLs are too big, they basically can't get through, but the small LDLs can get through and get into the intima here, and you can see right here where there's an oxidation process that can occur. And I'll go through this scenario many times so you get the idea, but the small LDLs are going to go in by a concentration dependent manner. Basically, they're going to be high concentration here, low concentration here, and because they can diffuse through, they will get through, they will become oxidized, especially if you have a high free radical number, if you have high reactive oxygen species, all of those, you're going to oxidize those LDLs. The macrophages, I'm trying to find my little pointer, the macrophages are going to come in, they're going to gobble them up because they think they're foreign. They're going to form what's called a foam cell with several LDLs in it. They're going to get big and fat like a tick, on a dog or something, and then basically they're going to burst. There's going to be an introduction of protein and calcium, and then they are going to become hard, and that's what we call plaque. And then what you see is it's starting to get bigger and close off the blood vessel, and this just continues to get bigger and bigger and bigger, and so that's when we cut off the oxygen supply. But so anyway, but you'll notice the normal LDLs and medium just go on. They don't get embedded into and become part of the plaque. So we'll talk about this over and over again because I want you to get the idea. But here's the idea, is that the small LDLs are going to go in, and they're going to go into the intima and become trapped. And then, again, the concentration gradient is going to occur, and because they're small enough, they can get through. If you have oxidative stress, then those LDLs will be modified, which means that the identification marker is going to be oxidized. And what causes oxidative stress? High free radicals, high reactive oxygen species. We talked a little bit about those when we were talking about fats, and we were talking about oxidation and free radicals. So you should have a good handle on things that you could be eating or things that you could be doing that could maintain high free radicals or high reactive oxygen species that could oxidize LDLs. Now, if you don't have a high free radical level, you don't have high reactive oxygen species, then the LDLs just become trapped and they don't become part of plaque. They're there because of the concentration gradient, but they don't get attacked by the macrophages because you don't oxidize the identification markers. So it just depends on how many free radicals and how much reactive oxygen species you have, is going to be a big determining factor whether you form the foam cells and then eventually the plaque. So anyway, this is the same scenario, just a different picture that hopefully gets across the idea. But again, just to review, the reactive oxygen species are things that contain oxygen that can be very reactive. And some of them we get from everyday mitochondrial issues, from the endoplasmic reticulum, and some we get from the food that we eat, and some we get from not eating enough phytochemicals that are antioxidants, all of those key things that we would have. Here's just some examples again of reactive oxygen species, and they are basically missing an electron, so they become very reactive, and then they lead to oxidation. Here's some other ones, negative. I mean, there are some positive aspects to reactive oxygen species because they do help, as you see down here, with apoptosis, with cell signaling, and part of the immune system to help destroy bacteria. So there are some good things, but if you have an overabundance, they're going to basically attack and oxidize because they are missing that electron. They're going to try to find one and be very reactive. What can we do about it? Again, we can use antioxidants. We can have vitamin E, vitamin C, the antioxidants dealing with polyphenols, which are phytochemicals, and that kind of thing. So again, just a statement that the imbalance of reactive oxygen species and the body's ability to detoxify them with antioxidants is going to lead to oxidative stress, and that's going to lead then to oxidizing the LDLs and forming plaque. This is just again another set of table that basically shows lipid peroxidation in the LDLs will also leading to lysine residues that are going to be oxidized in the B100, leading to the plaque. So just several slides that basically say the same thing. And this is going to, so the scavenger cells have basically a receptor for the modified LDLs, and so they're going to fit into that receptor. They're going to be taken in by the lysosome and be broken down, basically, but eventually it's going to turn into plaque. Okay, and so here again is another just showing that ability of to form the foam cells with a lot of LDLs. They will basically burst, and then the protein and calcium will come in and make it hard. And it's underneath, I just want to stress, it's underneath this lining. It's not on top, it's underneath this lining, so you can't just scrape it away. And so here's where the plaque's going to form. It starts closing this vessel off, so you get reduced oxygen supply. Now, angioplasty basically is where they put a balloon in here, and they basically blow up the balloon, and they just kind of spread out. They don't reduce the amount of plaque, but they just kind of spread it out and open up this vessel, and then they put with a stent in there. That will keep the vessel open, and sometimes those stents don't work, but again, the hope is after that's done, you watch your diet and exercise and stuff to not make it worse, because it can happen in a different place where the stent's not. It can even happen in your carotid, so it reduces blood flow to your brain and stuff. So that's sometimes a doctor will check your carotids and look at the flow. But for this, we're concerned with the coronary artery, and so we showed this before. Okay, so where does nutrition play a role in this? Basically, the big players, the ones you want to watch out for, are the long-chain saturated and trans fats. They're going to be the biggies. They are going to affect the liver cell's ability to take up LDLs. And we'll look at how they are going to impair the receptor pathway basically by reducing the amount of LDL receptors. Therefore, you're going to maintain LDL levels in the blood. A lot of people think that saturated fats and trans fatty acids cause your body to make more LDLs or more bad cholesterol. Actually, what it does is it reduces the ability to take it out of the blood, so it maintains a high level of that. The worst saturated fats you can eat are the 14 to 16 carbon length saturated fatty acids. Those would be fatty acids that are in dairy product. Dairy products, dairy fat is considered the worst fat of all. It's because it's 14, 16 lengths, they're saturated. Beef saturated fat is around 12 carbons. It's not good, but it's not as bad as the 14, 16 range. And so there is a call for reducing that to about 7% of your kidney calories. I realize that on your diet study you're doing 10%, which is just worded it for the study, but if you had a risk for heart disease, they would ask you to get that down to 7%, and then your trans fatty acids below 1%. So let's look at the liver cell and see what these guys are doing. Again, what's going to happen is, what you want to happen is if you have an oversupply, the free cholesterol would use the ACAT pathway to reduce free cholesterol, esterify them, and store them. Okay, but long chain saturated fatty acids and trans fats, they reduce the going the wrong way. Sure, sorry. They reduce the ability of the ACAT pathway to do its job. So the free cholesterol cannot be esterified. It is not going to be stored. Therefore, you're going to have an oversupply of cholesterol, which is going to lead to the problems that we just mentioned before, is you're going to cause a reduction of the making of LDL receptors. So therefore, you're going to reduce the amount of LDLs taken in by the liver cells, and you're going to keep the level of blood LDLs high. So again, the long chain saturated fatty acids and trans fats don't cause your body to make more LDLs. They basically keep the free cholesterol high in the cell, therefore getting an oversupply, therefore reducing the amount of LDL receptors the liver will make, therefore reducing the amount of LDLs taken out of your blood. Your blood levels stay high, and so you increase the risk of plaque formation and that kind of thing. So that's why you should reduce the amount of long chain saturated fatty acids and trans fats in your diet to reduce the risk of heart disease. Okay. So the saturated fats are the biggies, especially long chain ones. The monounsaturated fatty acids, they basically are considered heart friendly. So olive oil is high in monounsaturates, and so that's why they promote olive oil, or canola oils are pretty high. So they have no effect on receptor pathway. They don't have a real high risk of oxidation because they only have the double bond. So they are considered heart friendly. So they will be positive. If you're going to eat fat, then that would, or oils in cooking and that kind of thing, it's still going to have 9 calories per gram, so it can increase obesity. But as far as heart disease, these would be considered heart-friendly fatty acids. The polyunsaturated omega-6, we need to limit those. As you can see, they have some negative effects. They can actually been shown to increase scavenger activity. They have a lot of double bonds. Omega-6s seem to be easy to oxidize, and so they can, oxidation is kind of like a snowball. It just keeps, if you oxidize the fatty acids, they increase risk of oxidation of their identification marker. There's some reports out that they increase clotting, which you don't want to do if you have heart disease. And so there is a call for a limit of those. And so polyunsaturated, again, would be corn oils, things that are vegetable or seed oil, corn oils, sunflower oils, safflower oils, cottonseed oils, those kinds of things. You'd want to limit those a little bit. They're not as bad as saturated, but not good like monounsaturates. Omega-3s, these are also considered good. Even though they're a polyunsaturate, for some reason they have a resistance to being oxidized. They actually thin your blood, so you have to be careful if you're taking omega-3s. I may have mentioned it before, I can't remember. If you're on like blood thinners like Coumadin or something, you have to be very careful with how much omega-3s you can take. And if you're taking omega-3 pills, again, 1 gram of the DHA EPA is probably the max you'd want to take, unless your doctor prescribes it more, because it can really thin your blood and you can become a bleeder and you can't clot your blood. And it has no effect on LDL receptors. So again, 500 milligrams of both of these, so 1,000 milligrams of 1 gram, or fish 2 times a week, fatty fish, so we've talked about this. Secondary goal, so our primary goal was to do whatever we could to reduce LDL cholesterol. Secondary target, if LDL cholesterol is not a problem. Basically, you have met your primary target, but if you look at metabolic syndrome and you have these conditions, you are just as high a risk as if you had high LDL cholesterol. So that's a secondary target, is to make sure that metabolic syndrome isn't an issue along with high LDLs. So again, you want your total cholesterol below, you want your HDLs as high as possible, above 45. You want your triglycerides as low as possible, below 150, and then your blood pressure needs to be fairly close to normal. And again, any 3 of these would put you at metabolic syndrome, so at just as high risk as if you had high LDLs. HDLs are considered good cholesterol. There's several things that they're good for. Basically, they can take cholesterol back to the liver and get it out of the system. They do have some antioxidant activity. We talked a little bit about inflammation. We were talking about lipids. Lots of positive effects. What can raise your HDL? Aerobic exercise is really the only thing that has been shown to have a significant impact on HDL numbers. Now, losing weight, stop smoking, all of those things have a minor effect, but aerobic exercise is the key indicator of what can raise HDL numbers. And so again, that comes to that aerobic exercise, 150 minutes a week, if possible, that you can get that done, because it will tend to raise your HDL numbers and do that. Again, how does HDL do this? Basically, this cholesterol ester transfer protein will basically help transfer oxidized lipids from LDL to HDL, so you can get those out. You actually can steal it from the LDLs, and so so it can reduce oxidation. It can do a lot of things, and so this is kind of an indicator. Here's your CEPT as part of the HDL, and so it can actually, you notice the little stars are the cholesterol things and the oxidation and all that. So basically, the HDLs, if you follow the arrow, can take from plaque that hasn't been hardened yet. It can't do anything with hardened fat, but foam cells basically that haven't burst yet, it can basically take some of the cholesterol out of them and then basically transport it around back to the liver. And then out of the LDLs, you can see that it does the same thing. So basically, HDLs will reverse cholesterol transport, or reverse the effects of some of the cholesterol or what damage it could do by getting it out of your system. So HDLs are considered the good guys. Another way that it can be an antioxidant, it has another enzyme in it that can actually reduce the oxidative modification of the LDLs that we talked about when the small dense LDLs get oxidized in the intima. And so I've kind of highlighted here, here's the peroxidase of the HDL, and here's the oxidized LDL, and it can actually take that out and be an antioxidant in that case. and not allow it to go the macrophage foam cell plaque direction, but also here's the peroxidase, and we can actually take some of the cholesterols and stuff out of the foam cell before it bursts and becomes hard. And so therefore you can reduce the impact of oxidized LDLs with the HDLs. So those HDLs need to be as high as possible, so that you can reduce the effects of possible oxidation of LDLs and making plaque. And this is another, just another blurb I got. Basically, it's going to protect against oxidative damage, but what I put this on mainly for is the HDL from obese patients was less efficient. So obesity can actually reduce the efficiency of HDLs. Because it reduces some of the activity, the hydroperoxide levels in the HDLs. And so obesity can have an effect on whether your HDLs will actually work good or not. So if you lose weight, it's not only will you increase your HDL numbers, but you increase their efficiency also. So that's another place where obesity becomes an issue. Antioxidants, I got this information from the Linus Pauling Institute, which is in Corvallis at Oregon State University, of course. But these are the levels that they would recommend to reduce LDL oxidation, because what you want to do is get rid of those free radicals and the reactive oxygen species. Vitamin C, vitamin E, beta carotene, they don't recommend supplementation. There have been some indications, some research that has shown that, especially in smokers, beta carotene can cause it to get worse. So there's no recommendation for beta carotene. Selenium is an antioxidant, so these are some recommendations for these. We kind of mentioned it before that vitamin C is water soluble, so it's going to do its antioxidant activity in the serum of the blood and your body, you know, the water levels of your body. Vitamin E is fat soluble, so it's going to work in the plasma membranes of your cells and the basically the membranes of the blood vessels to prevent oxidation. So but there is a limit to vitamin E, and there's some skeptics out there whether vitamin E actually, you know, the supplementation actually works. They know it works as an antioxidant, but whether taking more is going to do any more, there's some debate on that. Kind of last thing is that, you know, it used to be back in the 70s when cholesterol, you know, 77, as we mentioned, cholesterol became a word back then, is that cholesterol was associated with red meat, and so they, you know, started recommending reducing red meat intake, and they still do. But it may not be because of the cholesterol levels in the saturated fat, because we said the saturated fat was 12 carbons and the 14, 16 were the worst ones. But what they're now looking at is possibility of the amount of iron that's in red meat, because that's where we get a bulk of our iron. And so there is a recommendation for men and postmenopausal women, because after menopause, then women have basically the same risk factors as men. And so excess iron overload can cause, basically it can be an oxidant, you know, it can cause oxidation, and it is considered cardiotoxic, which means it can affect heart cells and become damaging, causing inflammation and oxidation of LDLs and that kind of thing. So they're thinking now maybe it's not the saturated fat, maybe it's not the cholesterol, maybe it's the iron that's doing that. The other thing you'll find is if you look on vitamin supplements that are good supplements for men, they will not include iron as a part of the mineral content of that vitamin. And then postmenopausal women's vitamins will not have iron. If you look at the ones that are good vitamins that have been researched and that kind of thing. And so if you are a man, or if you are a postmenopausal woman and you are taking supplements, you should look on your vitamin mineral supplement container and make sure one of the ingredients is not iron. because it could increase the risk. So the recommendation is no supplementation of iron for men or postmenopausal women. Okay. This is just kind of shows how iron can be part of transferrin, which transferrin transfers iron around. It gets into part of the cells, and then if you have an iron overload, it can become an oxidant inside of cells and that kind of thing. So anyway. All right, so thank you for listening to the cardiovascular issue, and I hope we taught you something, and hope you can carry this out and inform some other people about what they should do. All right. Oh, I guess I had one more. Basically, this is just showing oxidation of the iron. Okay. See you later.